So I'm Luca Troise. I'm working currently at the physics department of the Technical University of Denmark. And my talk today will be about what I've been doing in my PhD in the last 2-3 years. So what we mainly are trying to do is to sense biological signals from biological samples such as mice or rats or frogs. And to do this, we use a magnetometer that is based on NV centers in diamonds. So just to lay down some numbers, probably everybody has already seen this at some point. The biological signals that we are interested in span in the range between a few femtotesla to a few nanotesla. And with our current sensitivity with our diamond, we can reach around 50 picotesla per square root hertz. And this allows us to be able to measure signals that are generated from action potentials from muscles. So that's why we are trying to measure now from mice. But our hope is at some point to be able to measure the spontaneous activity from brain using diamond and NV center. But for the people that are not working with NV center, I will just give a quick introduction on how NV center works. So NV centers are nitrogen vacancy center. They are defects in the diamonds. So two atoms of carbon are substituted with a nitrogen and with a vacancy. And this creates a very particular electronic structure, but I will not go in detail on how it works. If we shine green light onto a diamond that has NV center, we get out red fluorescence. And this red fluorescence can be quenched if we sweep a microwave field around 2.87 gigahertz. And we found a resonance in which this fluorescence is quenched. But this resonance is also magnetically sensitive in the way that if we apply a magnetic field, this resonance is shifted in the frequency spectrum. So we need to find a slope in this resonance that would be our most sensitive point, fix our microwave field around that point, and see the movements of the frequency of the resonance around this frequency. So usually people do standard electrophysiology, and standard electrophysiology consists on having a stimulation pulse that is given by an electrode that needs to be in close contact with the tissue we want to investigate. In our case, this is a mouse hippocampus. And in order to read out the signal, we need a bipolar electrode that also needs to be in close contact with the muscle. As we can see, and it's easy to understand, the stimulation is invasive, because we need to be touching the muscle with the electrode, and this only a small contact can damage the tissues in the point that we are interested. Also, since we are sending a stimulation pulse, this will come exactly as it is inside our readout. So we will have a large stimulation artifact that is sometimes very hard to get rid of. Moreover, there are also capacitive effects due to the fact that we are touching the tissue with a metal, so the shape of our signal can be modified by this. So in 2015, there were two papers that came out, not from us, of course, that introduced the field of optogenetics. In this field, we don't use a stimulation electrode, but we use light to start a contraction inside the muscle. And this is due to some modification in the genome of some mice that we can obtain due to this channel rhodopsin protein that acts as a light-gated ion channel, meaning that as we stimulate the muscle with blue light, it will activate an action potential and therefore a contraction. I maybe have a video I can show you of how it works. Hope everybody can see it. So we are simulating this small muscle that is in a solution with a blue light. And as soon as we stimulate it, it will contract. I don't know if you are able to see it. I hope so. So we do this, but in our magnetometer setup. So going back to our presentation, I will go through how do we do this in our lab. So we have the muscle and we place it on top of our diamond. And at the same time, we do simultaneous probe electrodes recording. So we can have a comparison between the magnetic field readout and the electrical field readout. And we stimulate the muscle with a 450 nanometer LID or a laser. It depends on what we want to do. And the diamond is illuminated with a 532 nanometer laser and with a power between 1 and 2 watts. And with 1 or 2 watts of laser power, we get around a few milliwatts of fluorescence. So In our case, we are using this muscle that is called the extensor digitorum longus. That is a muscle that comes from the leg of the mouse. It has quite a strong contraction. So this is how the setup looks in real life. So we have two hooks in which this muscle is hanging, and they can be pulled to stretch the muscle on top of the diamond. The diamond is not clearly seen here, but it's just under the muscle, and the muscle is contained in this 3D plastic chamber that is printed in our department. And there is a solution in flow to keep the mouse alive, and also this solution is oxygenated. So these kind of measurements can last for up to 20-24 hours, and the magnetometer stays stable for 20-24 hours very easily. And the blue dots on top of the muscle is where we are simulating with a focused laser beam. And the solution is kept around 30 degrees for optimal biological temperature. So our diamond, between the specs of our diamond, it's an electronic grade diamond with a 20 micrometer layer of MV centers with a concentration between 0.1 and 1 ppm. It's not a very homogeneous diamond because it has some patches in which is more sensitive. And we can get an ODMR line width of 1 megahertz and a contrast of approximately between 1.5 and 3%. So in our experimental setup, we have the fluorescence coming out from the diamond, but we can put a beam splitter in our setup and get a reference beam out of the beam splitter and send it to a photodetector that is a common mode rejection photodetector. It's electronically balanced, meaning that the amplitude of these two signals are automatically balanced by the electronic circuitry with a bandwidth of a few megahertz. And the signal then is sent to a lock-in amplifier. We do hardware lock-in detection, and then it's digitalized. So we are modulating our microwave in order to be able to do lock-in detection. And if we can see here on the right, this is how normal resonance looks when we do AM modulation. While if we do FM modulation, our resonance will be proportional to the derivative of our signal. In our specific case, we do a downmixing of our main frequency that is around 2.87 gigahertz with a side frequency that is 2.16 megahertz. That is the frequency of splitting of the hyperfine lines of the NV centers. In this way, we can get a slope, so a sensitivity that is 1.5 to 2 times better compared to a single frequency drive. So now let's get a bit to the magnetic recording and to the processing. So if we record 60 seconds of measurement, that what we see is mainly noise. And we usually stimulate our sample, our muscle, every 10 seconds. That is a good biological rhythm for stimulation. And this is a normal photocurrent recorded after the lock-in measurement, and this is a raw measurement. So if we zoom in, we can see that it's mainly 50 Hertz and 150 Hertz noise. So if we look at the frequency components here, we see that it's mains noise, 15 kilovolt power line, and 16.7 hertz. So there is a lot of noise that comes from mainly the lab environment because we are working in an unshielded room. But the good thing is that our detector doesn't saturate even with 100 to 200 nanotesla of magnetic noise just coming from the power lines. And if we see the spectrum on the right, this is a measurement for around 10 hours, and we can see that the noise is constant in this frequency, but it also moves a bit around. So in order to be able to extract a very small signal that is around 100 picotesla, 200 picotesla from a noise that is more than 200 nanotesla, we use a small trick that is a whitening filter that is also being used in some models for the gravitational waves. The thing is that it can be used only when your signal is much smaller compared to the noise floor. So just taking the Fourier transform of your signal and dividing it by the PSD that is calculated through the Welch method, and then inverse Fourier transforming it, it's able to remove almost all the correlation from our signal. And averaging this for about 10-20 hours gives us a sensitivity of 10 picotesla standard deviation. So we can see here, this is a single trace recording of photocurrent. Mainly it's 50 Hertz and 150 Hertz noise, but after filtering we get from 200 nanotesla STD to 10 nanotesla STD. So this is an example of our recording. This is a work, it's an archive now, and on the left we have an example of the contraction of the muscle without any inhibition factor, because it's possible to add a drug that is called BDM in order to inhibit the contraction of the muscle, but at the same time generating an action potential. So you will have a signal, but you will not have the artifact from the movement. So the electrical signal and the magnetic signal look quite much alike. There is a bit of shift in time, but this is just given by the placement of the electrode and the diamond along the muscle. And then on the right, we have the muscle movement with the muscle with the contraction inhibition, and also looks pretty much the same. So this work goes on the same line of the Berry paper published in 2016, where the magnetic field was recorded from a giant axon, and also from the Jensen paper in 2016, in which the sciatic nerve of the frog was measured with an atomic magnetometer. The idea is that NV centers are not as sensitive as other magnetometers can be, as squid or as atomic magnetometers, but they have a very good property, that is a high spatial resolution. So the idea is to move towards imaging with NV centers, and in order to do this, we need to overcome some problems that are mainly given by camera limitation and brightness of the samples. Also, last year we published this work. We made a compact magnetometer that is 7 by 7 centimeters, and it fits in a small box with a sensitivity of 1 nanotesla. So I want to thank my group, my professor, that is Ulrich Andersen, and work in the lab has mainly been done by James, me, and Nikolai. Jan Meyer and his group that has given us the sample and the diamond, and Jean-Francois and Nikolai that take care of the biological part, while Axel and Christopher take care of the modeling system. Thank you very much. If you have any question, you're very welcome to ask me.
So Luca, wonderful. Thank you for your talk. There are 119 people now in the conference, so although you don't hear any claps, you should imagine them. And there is already the first question in the chat. Maybe you can read it again, like on your own, and react on that. Do you have the chat available in front of you, or should I read it for you?
Yes, no, I can read it. Could you kindly explain the idea of the noise whitening technique again? Yes, we can go back to the slide maybe. So the idea is that if you have the Fourier transform of your signal, and then you evaluate the PSD through a Welch method, so through windowing, it's like doing a lot of fast Fourier transform. In this way, you have a good estimate of your noise, but all the noise that is not correlated will not appear in your PSD. So if you have an impulse like a signal that is not periodic and is not correlated, it will not be cancelled by the division of the Fourier transform and the PSD.
Okay,
how many averages do you use to get a reasonable signal to noise ratio in your measurement? So we stimulate our sample around 10 times per minute. And in order to get a good signals to noise ratio, let's say of 3-4, we need I think 100 to 200 minutes of stimulation. So around 2 hours, 3 hours to get a signals to noise ratio of 3 or 4. What are the spatial dimensions of the diamond? And do you see spatial or temporal effect to its dimension? So the spatial dimensions of our diamond are 2 by 2 by 500 microns. And we see spatial temporal effects only in the way that when we put the electrode onto the muscle, they are not in the same place in which the diamond is most sensitive. So we see a delay in time between the electrical readout and the magnetic readout. But besides this, we don't see any distortion in the signal. Is there kind of a bias field you're using? Yes, we use 2 permanent magnets that are put at the side of the diamond with a field that is in the order of a few millitesla. Is the 532 nanometer isolated from the muscle? Would be 532 nanometer light activate the muscle? No, because we have the diamond that is on the bottom. Then we put aluminum foil as a reflector on top of the diamond, and then we cover it with tape. So it's also electrically insulated. And since 2 watts are quite much of laser power focused in 100 micrometers, you will get also a lot of heat. So the solution and the aluminum foil is a good heat dissipator for this. How much heating do the 1 to watts leave on the diamond? Yes, that's what I mean. If you don't put any aluminum or any solution, you can get up to 50-60 degrees on the diamond, and that will kill your muscle. But if you have the solution and a good thermal coupling between the diamond, in our case, the diamond is inserted inside a aluminum nitride plate, and it is covered with aluminum. So this acts as a good heat sink and doesn't kill the muscle.
Yeah, the mouse. I think the mouse is dead already.
The mouse is dead, yes.
Okay, I think there is Arne's question is still open, is it?
Which one is it? What was the golden material and what are its magnetic properties? Golden material? I'm not familiar.
It's like it's Kapton tape, so yeah.
It's Kapton tape, yeah.
Oh, okay. But do you also use it to block the light?
No, we use aluminum to block the light, and then on top we put Kapton tape. So it's around 100 micrometers distance between the diamond and sample.
And do you have problems due to the aluminium?
No, actually it's very good because it acts as a reflector both of green light and red light, and also as a heat sink. So it has many good properties.
And it's not thinking of microwaves.
No, it's very small paramagnetic, so it doesn't give any problem.
But it's a pretty good conductor.
Yes, but then we put Kapton tape on top, so we separate the aluminum from the muscle.
I think it was meant as a heat conductor.
Yes.
No, it was actually meant as an electrical conductor. Like if you put microwaves close to aluminum, I would expect it to distort or reflect microwaves.
For how our microwave antenna is built, the field is very concentrated in the center and just hits the diamond. So it's let's say 3D printed in the way that the field is very concentrated in the center and where only the diamond is.
And okay, if I may, I have two more questions.
Sure.
Go ahead. One is from Yorgos, who is working in our group on a similar thing, and he is wondering about the compensation of green intensity fluctuations that you showed there briefly in one of your slides. How do you?
Yes. Since this, I can go back maybe to the slide. So this one, we see a lot of DC drifting, but this is very slow compared to any measurement we want to do. So we just filter it out with a high pass filter around 220 Hertz.
No, I meant actually like your experimental setup. You have the red fluorescence, and then you have this common mode rejector.
Ah, yes, this one.
And
yes.
And I mean, how do you change the power of the green? I assume with an AOM, and how do you like take? I mean, there are quite a few different transfer functions, and how good is your compensation if you want for green intensity noise?
So the green intensity, let's say the general power is decided by a halfway plate and a beam splitter, so we can change the power going inside the detector. But the fine adjustments are done by the detector itself because it's electronically balanced. So with a bandwidth of some megahertz, it's able to compensate the same amplitude. It has an amplifier inside, so with a feedback loop. So it amplifies the signals and match them, and so subtracts the photocurrents.
Do you have a brand name?
Yes, it's a Nirvana detector from Newport Inc.
Thank you.
This is 125 kilohertz only.
Ah, okay, it's not megahertz. Okay.
Yeah, just two.
But, yeah.
So I think in principle, like I also have many more questions, but I think at a certain point we have to cut off. Thank you once more. Of course, like everybody's welcome to also kind of feed more questions in. Maybe you are able to kind of react on the chat after the conference, or at least after today's conference.